Swayam Prabha. Digital India. Educated India.
Okay, dear students, today again I will start the signal amplifications, but in these lectures mainly I will show the applications, different ultrasensitive biosensing applications using redox cyclings. Let's come. So, today's main concept for this lecture is the special examples using redox cycling and their applications. So, there is lots of applications. So, I will recommend, generally you can see in my slides, I put many references. You please go through all the references, then you will get the more details. But I will cover all the basic part in the lectures, but if you want more examples, please visit the link also. Different link, also different references I put in each slide. So, main keywords in the lectures is the electrochemical redox cycling and a lateral flow assay. I will give you one very special example of the lateral flow assay. So, you can search the lateral flow assay based on the redox cycling, you will get the many report. Also electrochemical redox cycling using the device like different kind of electrochemical device development, that also you can search. Okay. Okay, let us come the example here. So, here a special example, like you can see interdigitated array electrode we developed here. You can see, so here one electrode and here another electrode. So, ITO indium tin oxide coated electrode, where actually we modified some electroactive species like the ferrocene. Fc means the ferrocene, we modified here. And we modified the primary antibody on the electrode surface. But these two electrodes, either two interdigitated array electrodes. So, one will behave as a, where one behave as a anode, one behave as a cathode, where one will apply positive potential and another electrode will apply the negative potentials. I mean something different design that we can make, no, that is just for example I am saying, not just like the like one sensor surface and then redox cycling like this. Means in this case again we can reduce the number of the chemical by using just two different electrode, just kind of like a sandwich here, like two electrodes we can use, just one for where we can apply one positive potential and another electrode where we can apply the negative potential. So, where we are applying the negative potentials, that will behave just like a, like we do not want the reducing activity they can supply, no, something like this. See, this is the sandwich assay that already form on the surface, and APP, that is the substrate, react and form the AP, right. So, this AP can be oxidized, this AP can be oxidized on the sensor surface and it will release the electron. So, this electron release, right. So, here oxidation happened, right. So, in this electrode surface oxidation happened. Now, see the and here, so in this case the electron release, and in this case here you can see here we are giving some electron, right. So, here reduction happened, right. Reduction means electrochemically we are reducing. So, you can see in this this electrode, in this electrode AP actually oxidizing, see it is oxidizing, right. So, here oxidizing and here reducing, means in this case means we do not need any extra reducing agent. So, AP actually forming, AP forming based on this ALP reactions, then these AP can be oxidized and form the quinonamine, and this quinonamine can be reduced not by T-shape, right. Last time I told, can you remember, like aminophenol can be oxidized on the sensor surface, form the quinonamine, and that quinonamine can be reduced by T-shape, right. This is a reducing agent, but here we are not using any extra reducing agent. Here we are actually this quinonamine actually reducing by here applying some negative potential. Suppose minus 0.2 volt we are applying, for example. So, if you apply negative potential, it getting the electron and it will be reduced. So, this is one special examples where you can design something different, different redox cycling based biosensors. So, you should know like how we can design different redox cycling method. See another example I will show you here. So, in this case, say again this is the primary antibody 1, and here we use the like 2 antibody, there is a secondary antibody, and they have the secondary antibody actually conjugated with beta galactose. This is the enzyme, right. This is the enzyme based biosensor. So, this is enzyme, okay, and APG, this is just a beta galactose enzyme substrate, and it will form the aminophenol. This aminophenol is forming, right. So, here we can design something biosensors, like see here like different working, this is the all the our sensor surface, working 2, working 1, working 2, working 1, where working 1 where we are actually oxidizing the species. So, aminophenol is producing that, actually we are oxidizing, and quinonamine can be reduced in this working electrode 2, it is reduced and form the aminophenol again. So, like this way means we can design something different sensor surface. You see here in this case like if you have any silver plus in your solution, like silver, you have silver nitrate Ag plus. So, you can form on the sensor surface by using some reactions, you can reduce this silver to just silver Ag0, and then it can be oxidized. So, this can also help to form the biosensor. This example I will show you. I will show you one design how silver can form and it can generate the signal again. That redox cycling I will show you here. So, this redox cycling example is this D, you can see here. Suppose you have a biosensor like this. So, here, so you know this one I already told you, like this is the avidin coated, like this is the avidin, and your antibody already conjugated with the biotin, right. So, this biotin-related antibody you immobilize on the sensor surface, and this is your target. Now, your antibody 2, that is your secondary antibody that conjugated with alkaline phosphate, right, ALP. So, that will react with the APP and form the AP aminophenol. So, that you know already. Now, as I told, so this one AP aminophenol NH2 OH. So, it you know this can form easily quinonamine, right. This can form easily this one. So, it can just release the electron, it can form this. If you give the electron, then it will form this, right. So, like this way it will actually participate in the redox cycling reaction. Suppose you have Ag plus in the solution, like silver nitrate, whatever. Ag plus means some salt like silver nitrate, something like that. So, Ag plus is coming here. So, silver nitrate, then it will oxidize the aminophenol, right. So, it can oxidize to quinonamine Qy, and itself will be reduced to Ag0. This Ag plus will form Ag0 by the help of aminophenol. So, this is another redox cycling reaction, right, something else, but the concept is same, like EC redox cycling, ECC redox cycling, something like this, but here something different way we are trying. So, here we are just use a salt, silver salt. This silver salt will react this aminophenol and form the silver 0. But this silver formation means if you make so many silver particle on the surface, then you can easily oxidize those, that I will come, and you can apply some potential, or maybe you can run some electrochemical other signal, and you will get the signal. Means if you have the less number of silver, maybe you will get one signal. If you get very high number or many numbers of silver, then you will get the higher signal, something like this. So, if you have more Ap, then more silver plus will form the more silver, right, on the surface. Like if you, so that corresponds to, that's why target concentrations. If you have more target in the sensor surface, then more ALP on the sensor surface, right, and more ALP means more APP will react and form the more AP. So, number of AP will be very high, and more silver plus will form the silver 0, clear. And this we need like AP should be regenerated, otherwise AP concentration will be slowly it will decrease. So, how we can form the AP? Just we can use the reducing agents. Here NADA is actually acts as a reducing agent, nothing else. So, this was used reducing agent. So, this again aminophenol will form, and this aminophenol again will react to the silver 0 and form this. So, this reaction, that is why we need some incubations. When this kind of EC or ECC redox cycling will form, we need some incubation time, incubation. So, how long? Like 5 minutes or 10 minute incubation we need. So, during this time this reaction will happen, and you will get the silver on the surface. Now, let us turn on your electrochemical technique, you will get the signal. Okay. So, like this way you can apply this kind of redox cycling reactions for your biosensor development. Why? Like if you like just I told you. So, based on the concentrations, the silver will be different. So, you can use. Okay. Now, I will come a very important and very fancy examples of the lateral flow assay. So, what is the lateral flow? Laterally flowing the solutions, right? It is just a paper based sensor. This is a paper based sensor. We are using different kind of cellulose membrane, and one good example of this lateral flow assay that is already available in the market, the pregnancy test kit, but that is colorimetric, that is not electrochemical. So, there we just where you can we just drop the sample one part, and because it is made by paper, you know, is there, if you see the paper structure, if you see the microscopic structures, there is lots of like different like this kind of random like kind of threads is there. So, and because of this why you are facing lateral flow in the paper, because there is a kind of, it is called like a microfluidic kind of. So, it is called you can say this all the channels they will help to flow like from one part of the paper to the another part. So, this is lateral flowing. This is the kind of microfluidic, or you can say it is kind of flow that is helping the papers. So, I will refer, please check the microscopic image of the paper, that will basically help you why actually liquid flowing from one end to another end. So, if you draw off your sample on the one end of the paper, so basically because of the lateral flow it will start. So, you need different kind of chemicals as I told. So, we can design a electrochemical lateral flow assay. So, pregnancy test kit kind of things, that is also lateral flow assay, but they are colorimetric, they are showing the change of the color, that will come. But first I want to show you the electrochemical lateral flow. For the electrochemical case, I always saying we need some electrode, one is working electrode, one is reference electrode, one is the counter electrode, right. So, here on the working electrodes, there we actually immobilize our capture, our antibody, right, our receptor. Capture means the receptor. So, as for example, like antibody. So, they immobilized on the working electrode on the paper, and we can make a paste like reference electrode that is made by like silver or silver coated paste, and if counter electrode also we can make like something by using something like carbon base. So, this kind of 3 electrode system we can make on the paper. So, this is the sample pad, this is the sample pad on the lateral flow where we just drop the sample. It can be blood sample or it can be urine sample, it can be plasma sample, anything. So, this sample will contain the target. So, if its target present, then it will also flow through your paper. See, here some compartment you can see. So, here one compartment, this is called a sample pad, this is another compartment, this is called a reagent pad. Because as you see, this kind of redox cycling will start on this paper based lateral flow assay, right. So, what is the starting reagent in this redox cycling? You can see that we use the galactose, one enzyme that is conjugated with the secondary antibody. So, ANGP is the enzyme substrate for the galactose that will form the AN. So, basically this is as it is substrate, it should be your starting reagent and it should be on the reagent pad then. So, this is the reagent pad. In this reagent pad we will use all the reagent. So, we have to find out first which redox cycling you want to use. I already taught you different redox cycling. Let us try to find out which redox cycling is the best for your work. Okay. So, you optimize that, all the optimization procedure I already taught. Based on this, you select some chemical. So, here I suppose we selected ANGP, one chemical. So, this is the starting reagent and ruthenium hexamine 3 plus is the starting reagent and here TCB is the starting reagent, right, that I mentioned many times. So, that is why I see I used here in the reagent pad ruthenium hexamine, ANGP and TCB. See. So, 1, 2, 3. So, these 3 mixture I use here. And always I told you also that they should not react each other. So, although I kept them as a mixture, but because they are not reacting, that is why I can keep them easily and it will be stable. If they react, then cannot keep. But it is the best way if you can keep them like lyophilized conditions. Like we can vacuum dry. You can put the we can make a this mixture and like a solution, and in the vacuum dry it means like a lyophilized condition if you keep, and we can go for a good packaging, right. In this lateral flow, if you buy packing test kit, if you see there the packaging system, we are keeping this all that kit inside a packet. This is a very good methods you are following. There is not much water, not much oxygen. Why we are following these things? Because they can destabilize the reagent, they can destabilize the these reactions, or this can destabilize the sensor. That is why we have to be very much careful. Packaging also very much important, and how we are storing the reagent. Okay. So, this reagent, all the things we kept, this is the reagent pad, and here is the detection antibody. So, here we can drop this detection antibody that is conjugated with enzyme. That also we can drop and we can lyophilize. Okay. So, that is done. So, your fabrications part of this lateral flow done, and this is the last part. This is the waste chamber. I mean, this is another paper just here, like excess reagent, excess fluid, everything can be absorbent pad. So, this is the absorbent pad where excess chemical, excess reagent, when they will start flowing from here, then they will come, they will absorb. So, this is the whole design of the lateral flow assay. Now, let us start the reactions. When I drop the sample, what happened and how we can measure the signal, right. Let us start this part now. So, let us remove the basic things that I taught. Now, let us come the mechanism part of the redox cycling on the paper. Okay. See, here once you drop the sample on the sample pad, then suppose it is a urine sample. Urine sample because sometimes you know the invasive method, non-invasive method. So, that I can show you first, the invasive and non-invasive. So, invasive and non-invasive. Invasive means it is like a painful method, like we need to prick your finger or collect the blood sample from like using needles. That is the invasive method. So, basically for point of care and for the user friendly method, if you really want to develop, that's why we are trying to go to the non-invasive. So in this case, no need any prick of the fingers, and no need to collect the blood sample using the needles. It is less painful, that's why, but almost no pain. That's why invasive means generally we need the blood. And also invasive, sometimes you can CSF, cerebral spinal fluid. So this kind of sample we are getting, their cerebral like we need very trained persons also. So collections of the cerebrospinal fluid also not easy. From the spinal cord we have to collect the cerebrospinal fluid, right? So like common person, like if I make some point of care device, if I keep home, and if you want to go for like test based on cerebrospinal fluid, like it's really difficult for me also, right? I mean, common people, laymen, they cannot use the cerebrospinal fluid. They should have some basic expertise, some basic training, and same thing for the blood sample collections. But at least the pricking of fingers are still good, but it is not always. Some people they cannot prick their fingers. Suppose the glucose test case, who are the diabetic persons, they have to prick their finger every day. You know how many times they have to prick their finger? Like before their meal, they have to prick their fingers, right? So every time, say the per hour, if they want to check their glucose, because without checking glucose they cannot take the food. It's kind of sometimes painful for them. Every day cannot prick. And mainly if you think about like sometime this kind of diabetic things, now you can see even in the very younger age also. So baby, so we cannot prick their little their finger daily many times. That's why we are thinking now let's approach to the non-invasive method. Non-invasive means we can go for the different kind of sample like saliva. Saliva, urine, that test you can go for the testing. Also sometimes people think like interstitial fluid just below your skin, if you can collect these samples also non-invasive way, but that is also not pretty easy. You have to use a micro needle. Sometimes people thinking like using micro needle and getting the interstitial fluid just under your skin, that is the interstitial fluid, that is also sometimes become invasive, but sometimes minimally invasive. So we can develop some micro needle like a band-aid you can put on your skin, and this needle actually will not hurt your nerve systems. So that's why it is not much painful. Just keep like a band-aid on your skin, and it will absorb the interstitial fluid from the skin, and in the interstitial fluid there is a glucose, there is other biomarker, that we can go for the detections also. So this is the different sample we can use for the lateral flow assay or for the sensor kit development. Okay, now let's come back to these mechanisms of the biosensors, these lateral flow biosensors. Okay, so I drop the urine sample that contain some target. Okay, so naturally this chemical, they will dissolve, right, and they will flow. Now if you have the secondary antibody and this, it is already contain target, so target will bind, right. If your sample contain target, then it will bind with your secondary antibody, right. Okay, then it will come to your detection region, like this is your region in the detection region where you have the working electrode, that where already primary antibody coated, right. So then your target will bind, secondary antibody will bind, that is galactose will bind, and this chemical also will come here. So naturally with this galactose, then I will focus this, then these reactions. So this reaction will start here. So galactose will react with the NGP, form the AN, and it will react this, then this redox cycling will start. Now here you can see the working electrode, reference electrode, counter electrode, these three we have to make a adapter, and we can add this one with a potentiostat. Potentiostat. This is the electrochemical analyzer or potentiostat that can help to measure the signal. So if the target is very high concentration, naturally then you will get this redox cycling very fast, and you will get the high current, you will get the high output, and you can measure this one with potentiostat. Similar like the glucometer, like if you drop the sample and if you have the high number of if you have the high concentration of glucose in your blood samples, you will get the you can see the value. Actually, we are getting the all the current that we are measuring by flowing the electron, that will show in your display. There's some numerical value showing. Similar way, we can use the IoT, that I will teach you slowly at the end of this course, that IoT enabled biosensor we can develop. So, how much current you are getting, that you can see that a digital value on the skin. Like you can use some similar something like just your mobile phone you can use. There you can use your app and just run the app, and then you can see on your mobile screen that how much current is generating, corresponds to that much current, it will show a digital value. Okay. So, this is the IoT enabled biosensor that we are saying. Now, see, maybe you have so after binding there have lots of secondary antibody, but your target is very low concentration. Suppose you have only one target. So, other excess one what will happen, then it will go through this and it will absorb on the absorbent pad. So, excess one will be absorbed on the absorbent pad, excess reagent will be absorbed on the absorbent pad. So, excess part will be here, and generally we need the, when we are forming the sandwich assay, as I mentioned, after this is the primary antibody, then your target, then your secondary antibody that conjugate with the label, and every time after adding the target we need wash, right, so that excess one can go wash out from the surface. After secondary antibody we have to wash, so that your secondary excess label antibody can be washed out, otherwise they can show the extra signal, background signal they can show. But in this case it is kind of wash free. Why? Because excess antibody, secondary antibody that conjugate with the enzyme, as this sample flowing, so excess one can flow and it will come to absorbent pad, right. So, excess one will not be here. Even after adding this urine sample or your sample, you can add some PBS buffer, extra PBS buffer you can drop to minimize the background current. Which can cause the background current? Maybe if you have the extra this secondary antibody, if it absorbs maybe some non-specifically here, it can cause the higher background current. So, if you can add some little bit PBS also, that you can optimize also. So, that can help to all the thing wash. You don't need extra washing step, that's why we are calling the washing free. We don't need extra washing step, just drop or add some PBS and you can wait for 5 minutes or 10 minutes. As I said, you need some incubation time, then only this reaction will be completed, right. So, after this you will see this signal on your portable potentiostat, or maybe in the mobile phone based, if IoT enabled some biosensor you can develop, that you can see. So, this is the lateral flow based assay, very good technology you can use. But this lateral flow also based, that pregnancy test kit is available in the market, that is the colorimetric. So, what technology they are using? They are here using some antibody that conjugated with gold nanoparticle. So, here they are using some secondary antibody conjugated gold nanoparticle, and if target come, so this gold conjugated all the antibody will be attached on your test zone, all they will be accumulated, so that you will see some reddish color. So, then if you see the color, then you will see the positive test, and they have some control region. Although control region means all the secondary antibody that conjugated with the gold, if you don't have target, so in the control region they all will come, they will accumulate in the control region. So, control region can confirm you that this sensor at least fine, is working fine, it is means this sensor strip is okay, control region showing. But that is the colorimetric strip that I can describe more after few class, but today just I am showing the electrochemical strip. This is just electrochemical strip. But you can ask me that why the colorimetric is the very pretty simple method, why I should go to the electrochemical. Because colorimetric is pretty easy, but sometimes if you have the very low concentration, you may not see the color. That is the point. But electrochemical case, if you say very low concentration also, that low concentration you can measure because of this signal amplification. That is the utility of the electrochemical method. That I will show you later again, very detailed showing. So, conclusions of this today's lecture, we can use the redox cycling that can be useful for different biosensor development. We can fabricate different applications that I showed a very good example, so lateral flow assay, or this can be useful like different design that I showed, like silver nanoparticle also you can form from the silver nitrate, different like you can go for different design, not only the sensor design, even in the chemical part also you can go for different design. Okay, so that's all for today's lectures, and thank you very much. I will show you more example in the next class based on these signal amplifications. Thank you.